In this video, we'll go over electric forces. Let's start with charge. Let's say we have a proton and an electron, two subatomic particles that exist within the atom. A proton and an electron have what is called an elementary charge E, where a proton, the charge of a proton, is positive E, which gives us 1.602 times 10 to the negative 19th coulombs. Meanwhile, an electron is negative E, which gives us negative 1.602 times 10 to the negative 19th coulombs. So a proton is positively charged, and an electron is always negatively charged. No exceptions. The total charge of any given object is positive or negative depending on whether we have an excess of protons or an excess of electrons, n times E for elementary charge, where n is any real integer spanning from 0 to infinity. Conceptually, that is the amount of excess protons or electrons that we have. Just like many things in physics, the total charge in any region, even throughout the universe, is conserved. For example, let's say I had a piece of silk and a glass tube. They have a total net charge of 0, so they're neutral. That means that the protons and electrons are evenly distributed across the surfaces of these objects. Now let's say I were to rub them together, right? So the electrons will be stripped away from the glass tube to the silk. That would give the piece of silk a net charge that is negative. So the silk will be negatively charged. Meanwhile, the glass tube will be positively charged. However, the total charge of both the piece of silk and the glass tube sums up to 0, just like before. Let's try our first example. A small plastic sphere initially has a charge of positive 4.8 times 10 to the negative 19th coulombs. The sphere is then touched briefly with a negatively charged rod, causing it to gain additional electrons until its final charge becomes negative 9.6 times 10 to the power of negative 19 coulombs. How many electrons were originally on the sphere? Well, we're going to know two things. We're going to know the formula Q is equal to positive or negative n times E, and know that E is equal to 1.602 times 10 to the negative 19 coulombs. Letter A, how many electrons were originally on the sphere? So if we're given an initial charge of positive 4.8 times 10 to the negative 19 coulombs, that means we have an excess amount of protons and a deficit of electrons. So if we know that our initial charge is positive, that means we have a surplus amount of protons. We have more protons than electrons. So if we figure out how many protons we have, excess protons, we would figure out how many electrons are missing. We use the formula Q is equal to, this time we have an excess amount of protons, so positive n times E. This will give us the total charge, given the elementary charge number, times n for the amount of excess protons we have. And let's solve for n. So we're going to solve for n. So we should get n is equal to Q over E, and we are dealing with our initial charge, so Qi. Let me actually... And that gives us positive 4.8 times 10 to the negative 19. Oh, mind you, this is absolute value too, since we're dealing with the amount of stuff. We're not really concerned with whether or not the charge is negative or positive. Divided by the elementary charge of each proton. So the 10 to the power of negative 19s will cancel out. And all we're left with is just 4.8 over 1.602. That'll give us about 3. if you rounded. So we have 3 excess protons, which means we are 3 electrons behind. Part B. How many electrons were transferred to the sphere during the contact? If the final charge is equal to negative 9.06 times 10 to the negative 19 C, we have a surplus of electrons. So we use our formula again. We plug in our final charge. And our elementary charge number. And this should give us about 6, which is 6 extra electrons. What is the total number of electrons on the sphere afterward? So based off of only the net charges that we are given here, we can only give the total number of electrons gained from the start to the end. If we started initially with a deficit of 3 electrons, we can say that we're at negative 3. We have 3 electrons below neutral, a charge of neutral. And at the end of the process, we have an extra 6 electrons. We have a surplus of 6 extra electrons. For a sphere to go from 3 electrons below to 6 electrons ahead, it would have to traverse from here to here, which means it went from negative 3 to 0, which is 3 electrons, and then from 0 to positive 6. So an extra 6 electrons. So the sphere gained a total of 9 electrons. Thus our answer is 9. So here we have minus 3. So we have minus 3 electrons. We have an extra 6 electrons. And we have a total of 9. Now let's cover electrostatics. Electro meaning electricity, and static meaning stationary. So in this specific case, we'll be looking into point charges that don't move with respect to the observer. There's the common phrase, opposites attract, like charges repel. This basically sums up electrostatic forces. For example, if I had a proton, which is positively charged, and I were to put it in proximity with an electron that is negatively charged, these two particles will have a mutual attraction. That is because they have opposite charges. However, if I had 2 electrons or 2 protons, because they have the same charge, they will mutually repel from one another. It's important to keep this in mind as you will need it for future problems. Now let's cover insulators and conductors. An insulator is a type of material that has a tendency to resist the flow of electrons. The more an object is an insulator, the harder it is for electrons to traverse through it. And this is because the atomic structures of insulators, to put it simply, are more tightly bound between the nucleus and the electron. So you kind of want to hold on to electrons much more strongly than other types of materials. Conductors are the opposite. Electrons do move freely around conductors because the atomic structure of conductor-like materials allow electrons to be exchanged from one nucleus to the other. So you kind of have this sea of electrons flowing through these atoms. An example of an insulator would be air or rubber. An example of conductors would be metal, or water. That is why it is dangerous to touch water when there is a plugged-in toaster, because the electricity would flow through the water to your skin, ultimately electrocuting you. A ground freely accepts or provides electrons. An example of a ground would be the Earth. Because the Earth's size is so large, the addition or subtraction of electrons is negligible to its total charge. So you might as well consider things that are grounded to be neutral, hence the Earth. Induction is the interaction of electrostatic forces without direct contact. For example, if I had a metallic sphere with evenly distributed positive and negative charges, so it'd have a net charge of 0, and now were to hover over it, a negatively charged rod, without directly touching the sphere, I would be able to repel the electrons onto the other side of the sphere while simultaneously attracting the protons. So without direct contact, I have polarized the sphere. One side of it is positively charged, and the other side of it is negatively charged. To be more specific, polarized is the process of redistributing electrons and protons in any given object to the point where one side has a net charge that's positive and the other side has a net charge that's negative. However, it's still important to take into account that polarized objects have a total net charge of 0, and that is because there is an equal amount of negative and positive charges. Objects that have been polarized are called dipoles. And like I said earlier, a dipole is an object that has a net positive charge on one side and a net negative charge on the other side. And again, like stated before, the total charge still comes to 0. So an example of a dipole is a water molecule. You have a negatively charged oxygen atom binded with 2 positively charged hydrogen atoms. So one side of the molecule is negatively charged and the other side is positively charged. Thus, you have a dipole. Now let's go over Coulomb's law. Coulomb's law states that the electrostatic force between 2 point charges is equal to K, Coulomb's constant, times Q1 times Q2 over R squared, where Q1 and Q2 are the point charges, and R is the distance between those 2 point charges, and finally K is Coulomb's constant, which is 8.99 times 10 to the power of 9 newtons meters squared per coulombs squared. So, to write on a diagram, you have an electron and a proton, for example, Q1, Q2, and R would be the distance between those 2 charges. And so the magnitude of the electrostatic force being exerted on these charges can be summed up with Coulomb's law. When working with more complex problems, it is important to know the vector form, which basically specifies the direction for which these forces are being exerted by these point charges. The direction specifically is given to us by the vector r hat, which is what you see at the very end of these equations. We can illustrate this with a coordinate plane that has 2 point charges on it, one on the origin and one somewhere in the first quadrant. The forces being exerted on these point charges can be illustrated with these vectors sticking away from each other. And not only do we use Newton's second law, which is for every action there's an equal and opposite reaction, but we can look at these vectors and notice that they are pointed in completely opposite directions to understand why the force being exerted on one point charge could be the opposite or negative of the force being exerted on the other charge. You can see r hat, the directional vector of magnitude 1, just points from point charge 1 to point charge 2 to represent the direction of r. Meanwhile, the other vector r is the actual distance between point charge 1 and point charge 2. Now let's go over another example. Let's say we have 2 point charges. One is negative, one is positive. so Q1 and Q2. And they are separated by a distance r. Let's say that Q1 has a charge of positive 3 microcoulombs and Q2 has a charge of negative 1 microcoulombs, and the two charges are separated by a distance of 0.15 meters. Letter A, is the force repulsive or attractive? Well, because Q1 is positively charged and Q2 is negatively charged, we have opposite charges, so thus the force is attractive. Letter B, find the total force being exerted on these particles. So the electrostatic force. So we'll use the formula. We don't need a vector because we're only dealing with 2-point charges and that's it. We plug in our numbers. We can multiply the 3 with the negative 6. And because we're dealing with absolute value, the negative sign won't matter. So we'll have 3 times 6, which will give us 18. And then we'll multiply the 10 to the power of negative 6's across from each other. So using the exponent law, negative 6 plus negative 6 is negative 12. So we'll have 18 times 10 to the power of negative 12. We divide 18 by 0.0225. And that should give us our constant K times 8 times 10 to the power of negative 10. Coulomb squared over meter squared. Now I forgot to specify that our K constant is in newtons times meter squared per Coulomb squared. So these will cancel out. And our answer should be left with newtons, which is perfect because we are looking for the force, and force is measured in newtons. When you multiply across directly, and doing that, we should get 7.192 newtons. Okay, next example. Two small spherical insulators are separated by 2.5 centimeters, which is much greater than any of their diameters. Both carry positive charges. One is positive 60 microcoulombs, and the other is positive 6.66 microcoulombs. A third charged sphere remains at rest between the two spheres along the line joining them. What is the position of the third charged sphere? So it's important to know that the problem states that the distance between these two spherical insulators are much greater than their diameters. So the problem is hinting to us that we can basically treat these spheres as point charges, meaning we don't have to consider the diameter or radius or any other measurements of the sphere itself. So let's write a diagram. We're going to measure the distances between these 2 point charges along the x-axis. We'll put the first point charge at the origin, Q1, and then we'll put the second point charge somewhere along the x-axis. We know that the distance between these 2 point charges is 2.5 centimeters. So we'll set the x position of the second charge to be 2.5 centimeters. For conveniency, let's convert that to meters. So the position of our second charge will technically be 0.025 meters. Now the problem states that the third sphere is located somewhere between the two other spheres along the line joining them. We'll label it as Q naught. We don't know where Q naught is specifically, we weren't given that. So we're going to just leave it as unknown. However, we will eventually have to find out where it is. That is what the problem is asking us. What is the position of this third charged sphere? Using Newton's second law, we know that the sum of forces acting on this third charged sphere are just the forces being exerted on it by point charge 1 and point charge 2. Because they all have positive charges, they will repel each other, but they will repel each other at different magnitudes. Q1 has a greater charge of positive 60 microcoulombs, so it will push Q naught with a stronger force than the force being exerted on Q naught by Q2. The problem tells us that the third charged sphere remains at rest. Given the equation force is equal to mass times acceleration, since it's at rest, its acceleration is 0, meaning it's not accelerating. So thus the forces would have to sum up to 0. This means that the force being exerted by charge 1 has to be equal to the force being exerted by charge 2. We are essentially looking for that sweet spot, that equilibrium, where the forces being exerted by Q1 and Q2 balance or cancel out, so that Q0 remains at rest. So because we're only considered with when the forces are equivalent, we only care about their magnitudes. So the negative sign is irrelevant in this problem. That is because we're not concerned with the direction of the forces. We're just concerned with whether or not they are equivalent. So I'll write it out in this diagram. Over here you have the force being exerted by charge 1. And that has to be equivalent to the force being exerted by charge 2. So from now on, we will be working with this equation. Force 1 is equal to force 2. We're going to plug in our Coulomb's law for each force. So the left side of the equation will be the interactions between point charge Q1 and point charge Q0, which is why we have Q1 and Q0 for the charges. And the right side of the equation will be the interactions between Q0 and Q2, which is why we have Q0 and Q2 for the point charges on that side. The K's cancel out. We can divide them both by K, and then Q0 cancels out as well. So now we're left with Q1 over R1 squared is equal to Q2 over R2 squared. R1 is the distance between Q0 and Q1, and R2 is the distance between Q2 and Q0. The reason why we are distinguishing these R's is because, again, the distances between Q1 and Q0 could be different than the distance between Q2 and Q0. R1 is equal to X0, because if you look in the diagram, that is a distance between Q0 and Q1. While R2 is just the distance between Q2 and Q0, which can be mathematically expressed as the distance X2 take away X0, as illustrated on this diagram below. So now we're going to plug these into our equation to be left with this. Our goal is to find X0, the position of the third sphere, so we're going to have to solve for X0. I'd start by multiplying both sides by X2 take away X0 squared to get this, and then divide both sides by Q1. That way you can further isolate X0. Then, because exponents are distributive, you can pull out that square and then square root both sides. And then on the top of the fraction to the left, I would factor out X0 because I'm trying to solve for X0. If this doesn't make sense to you, just imagine if you redistributed X0 to both of those terms, you would go back to where we had before, which is X2 minus X0. Now the X0s would cancel out, and I'll be left with this. I add 1 on both sides, and then divide by X2. Then I can flip the fractions on both sides, which is a shortcut for a long algebraic calculation, and this works for any other problem with fractions. So if I had 1 over b equals c over d, I can flip them to get b equals d over c. Now this is my formula that I could use to find X0. And before I jump to the next part, I'm also going to write 2 other forms of this same formula. So just in case you get confused, you're going to see 2 other equations for X0. Mind you, these are equivalent, and you can use any one of these 3 formulas that I will write down to find your answer. Okay, so I'm simply going to plug in my information now. I have X2, which is 0.05 meters. Now it's important to note down that the square root can give me both a negative and positive result. But the reason why I'm using positive is because if my X position was negative, that means that my point charge would be to the left of both Q1 and Q2, meaning that it wouldn't be at rest. It would just be accelerated to the left through the forces of both Q1 and Q2. And so plugging in all my information, I get X0 is equal to 1.9 centimeters.